So this is a talk about Elm, which is a functional language for web apps that's designed to be both easy to use, easy to learn, and but powerfully expressive still. So on screen, I have a snippet here from the new Elm guide. It just came out last week with Elm 0.17, and I recommend checking it out. It's really good. So in this talk, I'm going to focus on a particular part of Elm called signals. Signals are values that change over time, like an infinite stream of input. So it might represent the user's mouse position in real time, or whether they're currently pressing the spacebar, or maybe a timer that ticks every second. Those inputs are going to come in through a signal. And other languages obviously can represent values that change over time. So if you have like a variable and a loop, and you're updating the variable every time you go through that loop, you are keeping track of a value over time. You're maintaining state over time. Or if you have an event triggered every time you click something, that is a value that changes over time, if you're incrementing some value every time you click. But from the language's point of view, in most of those cases, the language doesn't understand that that value is changing over time. You know that because you understand the code, but there's nothing in the language itself that might prevent the pitfalls of working with things like that. It doesn't have any awareness of what you're doing. But in Elm, with signals, Elm's able to understand values that change over time at the level of the language and at the level of the type system. So I'm going to try to show you what that means and why it's interesting. So here's an example of a signal that's built into Elm along with its type signature. So there's a signal built into the mouse library called X, which is just the X position of your mouse in the browser window. And the colon just means has type, so the type of the signal is a signal of int. That's how you'd say it. And signal in this case is acting like a type constructor, which is kind of like generics in something like C# or Java or C++. List works the same way. So if you have a list of integers, you're going to say list int. So let me just show you what that looks like running. You can see it just tracks the mouse over time, and all I need to do to show it, it's a very short line of code because Elm is built for working with these. And so there's other signals that built into the mouse library. If I change it to position, that's both the X and Y coordinates at the same time. And so instead of being a signal of int, that's going to be a signal of pairs of ints. And you can see that reflected in the type signature. And so signals are a lot like observables, if you're familiar with libraries like ReactiveX or RxJS, CycleJS. All these libraries are based around this idea called functional reactive programming. And it has a bit of like a buzzwordy feel to it. But the core idea is really powerful and interesting. And it's that to think of your program as taking a stream of input and piping it through a bunch of pure functions to produce the output of the program. And so in Elm, that means taking multiple signals, doing transformations on them, merging them into a composite signal, maybe accumulating the values over time in order to represent state, and then routing the result of that computation out to, for example, displays, or maybe trying to do HTTP requests, anything outside of your program. So the original goal in this talk is to get you to this like aha moment where signals click for you, and you can see the elegance of the idea and how powerful it is for representing particular kinds of things. And I'm still going to do that, but there's a little bit of a wrinkle, which is that last week with Elm 0.17, signals were removed from Elm. And the title of the blog post announcing that is a farewell to functional reactive programming, making signals unnecessary with the Elm architecture. So that's interesting. I read that. I thought to myself, like, okay, maybe they're just unnecessary, but I can still keep using them. But no, definitely not. Everything related to signals has been replaced with something simpler and nicer. And what it's replaced with is a sort of global messaging system where your inputs, they post messages, and other parts of your program listen for them. So why was that change done? It's actually for pretty good reasons. So reading here, as the design of subscriptions emerged, we saw all the toughest concepts in Elm, and signals are one of those, could collapse into simpler concepts. So I wasn't caught totally by surprise by this because I had been following along with the development of Elm, but I still had to figure out like what to do for this talk. And so this talk's called Folding Time with Signals in Elm, but I think with this change, Probably more accurate title is that. But I'm still going to tell you about signals. And there's a few reasons why it's still worth thinking about. First of all, along with the explanation of signals, I like to go through sort of like an intro to the basics of functional programming, thinking about type signatures, thinking about maps and folds, which is useful to people who might come from Python, JavaScript, Ruby, normal web programming languages that don't necessarily think in those ways. And I think even if you keep on writing in those languages in your everyday work, you can still learn a lot from this way of thinking and bring it back to your work and be more productive, even if you're not using Elm. Another reason is that the new system that it's replaced with is actually not that different. And that's kind of something that I'm going to get into. I think the main difference is in the presentation of the idea to the beginner and to the programmer. But the fundamental thing that's going on when you understand signals, it still applies to the new system. And so I'm going to go into that. Plus, there are still plenty of libraries that keep investing in functional reactive programming, which I mentioned a few before, Cycle.js, RxJS. So what I'm going to do is I'm going to give a compressed version of all the parts about signals, and then at the end I'm going to talk about what they're replaced by. And so the short summary is that signals were better for making cool demos and talks than they were for building web apps, which, if you're being honest, web apps are mostly like forms and inputs. And there's a fairly narrow set of things that you typically want to do and organize them well. And there's very particular kinds of state that you want to manage and particular kinds of complexity that you want to manage. And signals are maybe more general of a concept than is necessary for Elm to be good at the things that it wants to be good at. So there's a kind of a good lesson here for people who make tools, is that the designer of Elm is being very clear in terms of the purpose of Elm and making changes to reflect that. So first, a little bit about me. Thank you. I am a front-end developer. I work at PayPal in Chicago. And like I said, in my day-to-day work, I work with JavaScript and Python. But I've still been able to take a lot of what I learned from Elm back to my work. And I'm not the only person to do that. So if you are familiar with React, for example, one of the most popular ways of keeping track of global state in a React app is a library called Redux. I should take this picture off the screen. That is explicitly inspired by Elm's functional reactive programming architecture. So these ideas have kind of permeated the larger web front-end sphere, and there's this sort of back and forth effect where now I think what Redux does has actually gone back and influenced Elm. So it's really cool if you want to leave the talk and go play with Elm, because it's wonderful. But that doesn't mean you have to then actually make your boss let you use it. Thank you. But first, let's talk about Plato for a second. So this is a quote from a dialogue from about 370 BC called the Phaedrus. And Socrates, in this quote, is talking about, as usual, what makes a good argument. And good arguments usually start from good definitions, which means having a clear understanding about what the argument is about, the things that the argument is about. So here in this quote, he's describing two things that definitions are supposed to do. And like a lot of stuff in Plato, it seems very simple, but then when you start to think about through the implications of it, it becomes clear that it's sort of a deeper idea than it seemed at first. So one of the things that a definition is supposed to do is see together things that are scattered about everywhere and collect them into one kind. So see things that are similar and recognize that they're similar. But the other thing it's supposed to do is cut up each kind along its natural joints according to its species, and trying not to splinter any part like a bad butcher might do. So an example kind of makes this clear. It's like if you're thinking about geometry and you're trying to make a geometrical argument, you might start by noticing that there are all these circles and squares and octagons and irregular shapes, but despite their differences, they're all shapes. So we understand that shapes have something in common with each other, so they're a single kind of thing. But within that kind, there's like lots of different subkinds, and there's a lot of ways of dividing them up. So you might divide up shapes by the number of sides. You might divide them up by whether their sides are all equal or whether their angles are all equal, or ellipses versus polygons. And all of those, it turns out, are like useful groupings that you can use to reveal deep truths about geometry itself, which is why you learn those particular groupings in school. They're the ones that have been borne out by people trying to use them. But you can also mess up dividing things up. You can also do it really badly. So you can divide shapes up by which ones are red and which ones are orange, which is not really going to be very useful. You can say, like, these are the good shapes that have more than 18 sides, and the other shapes with less than 18 sides are pieces of shit. So that's not going to help you very much. And so what Socrates is saying here is that picking one of those bad groupings is like what a bad butcher might do. It's like trying to carve a turkey, but instead of seeing like legs and thighs, you just say like, I'm going to cut it in half. I'm going to cut it in the bottom half and the top half. If you try to do that, you're going to have a lot of trouble, and you just end up with a big mess. And so getting things right conceptually up front is really important, and we do that in programming too. We have our definitions up front. We have the classes that represent the objects that our program's about. We have our database schemas. We have the types. And so this is a form of questioning that should be really familiar to us as programs. Do the set of definitions that we picked up front fit the thing that we're actually working with? And so I want you to think about signals from that point of view. How do they chop up the domain of web interfaces? And is the resulting division natural, easy to use, easy to think about? One thing that's really funny is that in the original version of this talk, the answer to that is obviously yes, signals are perfect. They're the right abstraction. But the changes in Elm 0.17 show that the answer to that question actually depends on like what you're trying to do and who you're trying to get to do it. So if you're really aiming your programming language at beginners, maybe you don't need something that requires a lot of thought up front in order to get it. And then maybe once it clicks, it's very easy to understand, and all the Haskell programmers in the world can show up at your language and understand it. That might not be the right thing if you're trying to make an accessible web programming language that you want many people to use. So now let's actually talk about Elm. So like I said, it's a functional language for writing web apps. It was created by someone named Evan Splitsky in his undergrad thesis, actually. And he's been working on it ever since for about 4 years. It's originally based on Haskell, and the syntax is really similar. So if you can read Elm, you can probably read some Haskell. There's a lot of stuff in Haskell, though, that is not in Elm. Elm is a lot simpler than Haskell. It's a lot more focused. Since it's focused on web UIs, there's a lot of stuff that's not in there. There's a lot of design decisions you can make, the designer can make, to take things out that are not needed if you're only making web apps. And that means that Elm's way easier to learn than something like Haskell, which has never been accused of being too beginner-friendly. Elm is, like Haskell, purely functional. So what that means is that functions in Elm are pure. Their input determines their output. If you give a function the same input, it will always have the same output. And functions can't look at any kind of mutable state somewhere else in the program. So you can't have a loop that updates a variable somewhere else every time it runs. And the reason for that is that all values in Elm are actually immutable. This is a really tight constraint on the way you program. And what's interesting is what it does is it enforces best practices in a way that makes them impossible to violate. So if mutable state is really dangerous, provide very detailed ways of handling it that, because of the compiler, you can't do them any other way. You can't mutate state. You can't say like, oh, just this once, I'm going to mutate this variable and leave it for the next person to figure out, because Elm just won't let you do that. And finally, it compiles to JavaScript, so you can actually run it in the browser. And the compiler is really strict and has some of the best error messages I've ever seen in a language. They're really helpful. They spot potential typos. They're so like, you spelled this, you swapped 2 letters. They notices that by doing fuzzy matching on variable names, things like that. And it tries to be really helpful. So how do you use it? The way you use it is just by taking an Elm file and piping it into Elm make on the command line. And you get a JavaScript file you can just drop on your page. And obviously there are plugins for Gulp, Grunt, Webpack, whatever you're using to bundle your JavaScript files if you're running a production site. So let's look at some Elm code. And I borrowed all these examples from this, the Elm syntax page on the Elm website, which is really nicely done. You've seen some of these already, but of course you have your literals, and they all have types. You have your booleans, your numbers, your strings, your characters. Nothing too interesting. There's a lot of ways to write lists. You can write them out literally. You can use ranges. You can use the cons operator, which is sort of an infix prepend. You can even build up lists with cons. This is sort of a normal thing in Haskell, but you don't see it very much in Elm. Not too much interesting going on with conditionals either, but it's worth seeing, especially for the examples we're going to see later. there's also a more complex case statement for a little bit more interesting logic. Records are kind of like structs, kind of like hashes, but they're not mutable. So for example, you can define an object that has fields x and y, and they have particular types. But when you update x and with that third line, that actually returns a new copy of the original value. So you can never mutate, even when the syntax sugar makes it look like you can. And you can also define a set of fields on an object and give it a nickname, like location, so we don't have to write line column every time we want to refer to this type. So here's how functions work in Elm. Function calls there's no parentheses, there's no commas separating arguments. The arguments are separated by spaces. And so in that first line, we're defining a function square that squares a number. In the second function, we're defining a function hypotenuse that uses the first. And you can see that in order to group square A plus square B so that square root is not confused about the spacing, we have to use parentheses to group those arguments. Similar with distance, we can pass in pairs to a function, and we can destructure those pairs in the definition. So we don't have to say distance, rt, and then in the function call in the definition, we'd say like the first part of r and the second part of r. We don't have to divide that. We can just destructure arguments. And there's also a really nice little lambda syntax because you're often going to be using map and fold, and you don't need to give square a name in order to pass it into map at the bottom. Pipes are an interesting example of a place where Elm tries to be user-friendly. So if you look at that dot definition, that's sort of a deeply nested function call, and in order to read it, you have to start from the right, which is kind of weird. You have to understand that we're making a circle, then we call fill it blue, then we move it to position 2, then we scale it to be double-sized. And that's not really the way that we think about it in practice. If we really think about it as a pipeline kind of that we want to feed our data through step by step. And what pipes let you do is kind of represent the exact same thing, but in a more readable way. And this isn't built into Haskell. I looked it up on Stack Overflow, and they're like, here's how you would write it yourself. That's typical. This is where things get a little bit interesting. So you saw those type annotations on the literal values, and they're pretty straightforward to read. And even on factorial, it's a function. So that says that factorial takes in an int, and it outputs an int. So that one's pretty straightforward to read. Add is a little bit more interesting because normally when you have a function that takes 2 arguments and returns a third, there's sort of a separation between the input arguments and the output arguments. And you're going to see why it's written this way in a second. So here's a little more interesting type annotation. That first argument to map, if you know what map is, I guess almost all of you have used map before, but I'll just say, it lets you apply a function to a list. So in the example here, if we have a function that converts ints to strings, and we have a list of ints, we're going to use map, and map tells toString how to apply itself to that list. So in the type annotation, we're saying we need a function from A's to B's and a list of A's, and we're going to come out with a list of B's. And those lowercase variables are type variables, which means they can be any type as long as the A and the A match and the B and the B match. So getting used to reading this notation kind of means like getting used to mentally putting in the types in the right spots. So that's what I've done with the labels there. So like int is A and string is B. So we have our list of ints and we have our list of strings as well. So here is why the arguments are not distinguished, the input arguments from the output arguments. It's something called partial application, which means that you don't have to pass in all the arguments to an Elm function. If you only pass in the first argument to add, what you actually get is a new function that only asks for the remaining arguments. So if I pass in 5 to add, I get this new function that adds 5 to whatever number I pass into it. And you'll see in a second that gets pretty interesting. So those are the basics. That's pretty quick, right? I want to use partial application to motivate a sort of different way of thinking about list map. And this builds it into understanding how signals work. Before, we thought of list map as a function that takes 2 things. It takes in a function and a list, and it outputs the list that's the result of applying that function to every element. But another way of thinking about this is through partial application. And you can see I added those parentheses around list A to list B. And the way to think about this is, if we only give list map the first argument, which is the function, what list map is doing is turning a regular function from A's to B's into a function that operates on from list of A to list of B. So you can think of map in the abstract as something that takes a regular function and it turns it into like a fancy function, where fancy depends on the kind of map that you're doing. So in this case, it's list map. So the kind of fancy is that now length can operate on a list of strings instead of a single string. So by calling list map length, we get this new function lengths that we can then apply to any list of strings. So here's an example of a different kind of map. And we're going to see why this was useful in a second. I'm going to cut back to the mouse example. And so in order to display mouse position, we had to feed that signal through signal.map and with the function show. And I'll show you why in a second. Oops. You'll notice that the type signature is really similar to list.map. And if you think about what listmap did, is it took a regular function and it told that function how to operate on lists, how to traverse lists. And signal map operates in exactly the same way. Signal map is what understands the internal structure of a signal and can tell a regular function how to work with a signal. So show is a regular function that takes normal values. So if I just write this is your sort of regular hello world. I should be able to refresh. And if I try to call show by itself, which is kind of like print, not quite, on a signal directly, all I get is sort of like, this is a signal. And that's because show doesn't understand the internal structure of a signal. And so what thinking about signal map shows you is that the line that we've drawn, is between sort of the internal structure of a signal and the functions that operate on its individual values. So once we think of it that way, it means that we can take any function that operates on regular stuff, like anything that displays something, and run a signal through it very easily using signal map. So in order to show the mouse position, we just had signal map show mouse x. But if we wanted to do something a little bit more complicated, most of this is not that important, but if you look at show rect, that takes in a pair, and it draws a rectangle at that spot, or with that size. So I have that right here. So right now, this is just a static function that displays a thing of a single size. If I change this to 300 by 300, I'll just get a square. But since we now know what signal map does, signal map tells this rectangle drawing function how to work with a signal of pairs instead of a single pair. And so to make it work, all we have to do is call it with signal map, and we get it running in real time using our mouse position. So those programs are cool. They're really short. I mean, they're elegant. And I like how they illustrate the analogy between list map and signal map, but they don't do very much. If you're going to have a UI, you need to keep track of what state the UI is in over time, and things that the user does are going to affect that state. So if all values in Elm are immutable, how can we manage state? How can we even have it at all? So there's going to be a similar analogy here. There's a pattern. Think about what list fold does, and I'll I guess explain it since some of you hadn't used reduce before. Reduce or fold is a function that collapses a list down to a single value. And a perfect example of that is summing the numbers of a list, adding them all up. And if you look at the type signature, what we need to do that, ignore the first one for a second, but just look at B, that's a starting value, and a list. So if we're going to add up the numbers in a list, we need three things. We need the list. We need the value that we're starting with, so 0. We're counting from 0. But then what we need is a way of combining each new element that we pop off that list into our intermediate total. So what's that combining function? That's addition. So when we pop 1 off the list, we add it with 0, and we get 1. When we pop 2 off the list, we add it with 1, we get 3. So add specifies just that little operation of how do we combine each new value with the total? How do we update our state with a new value and come out with a new state? And this is going to be an important pattern in the talk. If you look at the type signature of this function, it takes in this case, they're all the same. They're all just ints, but they can be different because of the A and the B and the B. it takes in our current total, a new value, and it outputs the updated total. And this is all it takes to add up a list of numbers. So if we want to do this with signals, it turns out signals have their own fold function that do the exact same thing. And remember the type signature of the update function. In this case, try to ignore the fact that it says AS there. But I'm following convention because the S is a normal way of a type variable for a variable that represents a state. So in this case, our new value that we're popping off the signal is the A, and our state is S, and the updated state is also of type S. So just like list fold, we need our combining function, we need our initial value, and we need, instead of a list in this case, we need a signal. So if we want to count mouse clicks, our starting value is 0. We're counting from 0 again. Our combining function, it doesn't add numbers. Well, all it does is it increments the state. So C, in this case, is our current state of the total. And each time we get a ping from mouse click, we're just going to increment C. We're just going to give it a new value that's one higher. And signal fold puts all these together just like list fold. And it keeps that state updated in real time. And what's interesting is that this is folds are, at least in the case of lists, they're a stateful operation, or at least a pseudo-stateful operation, that you can write in a way that doesn't actually use state. So you can take a fold, and I wish I had a slide doing this, you can expand it out using recursion so that there's not actually any state. It's actually a set of nested function calls. And that's how Elm can do this without having any mutable state. It basically simulates state, but it amounts to, in practice, actual state. So I didn't show you guys click count. My water fell down. But you can see that it works. There's not really much to it. So this is another example, and because the signal interface is common to these two signals, in this case, instead of a signal that fires whenever there's a click, it's a signal that fires every second. So I'm saying FPS 1, if I made that FPS 30, it would be 30 times a second. And you can see there's almost no difference. Because I'm ignoring, that's what this underscore means. I can ignore the actual value that comes in from the signal. All I care about is the fact that it pinged. And all I'm doing is incrementing the state. So I also have that one, I think. Maybe not. Huh. There we go. That's really exciting, right? So that adds some sort of context to what I said earlier about the idea behind functional reactive programming being thinking of your program as transformations on a stream of input. Do you have a question?
Yeah, mouse clicks, is that more like a factory that's generating those clicks?
In a way, and you can, oh, sorry, the question is mouse clicks is like a factory that's generating those clicks. Sort of, yeah. I mean, ultimately, this compiles to JavaScript, and those are actually just events. There's something that's listening for those events, and there's something that's triggering those events. But yeah, that's an appropriate way to think about it. So that adds some sort of color to the way that I said functional reactive programming wants you to think, which is that your program is a stream of inputs. You're doing transformations on them, combining them, accumulating them into state. Now we understand what that means. And maybe routing them to the appropriate places. So just to sort of cement that, I'm going to do a little bit more involved of an example, but I'm going to go through it really fast so we still have some time, because I only have 9 minutes left, to talk about what this system was replaced with and why it's not actually that different. So the goal here is that to make a little Mario character jump when I press the space bar. So I can just show you that running really fast. That's all it is. When I press space, he jumps. I'll click over to the code, but don't look at it yet. So what's actually required to do this? Well, we already know what fold P wants. And I'll say by stipulation, we're going to use fold P for this, because that's the only way to account for the state that Mario's in at any given time. Fold P needs an update function that tells us when a new piece of data comes in, how do we update the state of the program. It needs an initial state, and it needs inputs. So we're going to specify each of these. And putting them together is going to be very simple at the end. Once we get these constituent parts together, combining them is trivial. So our model just has Mario's y position and his y velocity. And his initial state is going to be standing on the ground, so his velocity is 0 and his position is 0. Type alias is like a nickname. So we're saying that whenever we're talking about model, we're talking about that shape that has a y and a vy, and they're both floats. This looks a little more complicated than it is. Our inputs, there's actually 2 inputs to the program. It sounded like the only input was me pressing the spacebar, but if we're running a physics simulation with Mario going up into the air, we actually need a tick on a frame rate in order to simulate how much he moves each frame. So there's actually 2 inputs. One of them is a tick. One of them is the spacebar. And what we can do is we can combine them into a single signal using this special map2, which takes in 2 signals and can zip them together into a pair. So our signal is going to be, instead of one or the other, it's going to be a pair that has both the time and whether the spacebar is being pressed. I did the same nickname thing, type aliases, so that we can more easily remember what we're talking about. So time is just a nickname for a float. The tick thing, what it does is it tells you how many milliseconds have passed since the last tick, and whether you're pressing the spacebar is Boolean, but we'll just call it key down. So the update function has 3 parts. Number 1, there's responding to when we actually jump. We hit the spacebar, and his velocity needs to be set to a number. 8 is sort of arbitrary, but you'll see that's just what makes it look right. But we want to set his velocity to 8 when we hit space. Gravity also needs to work. So when he's shooting up into the air, in each tick, we're going to reduce his speed, his velocity, by a little bit. That's gravity decelerating Mario. And the third one is that if he's already flying through the air, he has some upward velocity, we're going to move him a little bit. So each of these 3 parts, once we think about it this way, they're really simple to write. And look at those type signatures. That's the exact same type signature as the update functions that we used before. It takes in a new piece of information, that's a key down in this case. It takes in the current state of the model, and it returns an updated state of the model. So jump looks at space, and it says if we are pressing space, so if space is true, and if he currently has 0 speed, that means he's on the ground, we're going to set him to that vertical velocity. Otherwise, we pass the existing state through unchanged. And like I said earlier, that update to the record returns a new value. So it's not mutating state, that's just updating a new copy. Gravity has the same type signature, except instead of looking at space, we're looking at the amount of time that's passed. And so each tick, we're going to look at Mario's y position. If it's greater than 0, that means if he's in the air, we're going to reduce his speed by a little bit. We're going to move his velocity downward. If he is on the ground, though, we're going to set his velocity to 0, because if we didn't do that, he could keep flying through the ground. And finally, the physics is pretty straightforward. Each tick, we're going to take Mario's y position, and we're going to increase it by an amount that depends on how fast he's going. So if he's going faster, he's going to move a little more, and if he's going slower, he's going to move a little less. And that max 0 similarly means that he can't go below the ground. The lowest he can go is 0. And one thing that's funny is, remember, our input looked like a pair. It had that time key down signature. But what we can do is we can destructure that pair and only pass in the right thing to each one. So this pipe's syntax is a little bit hard to picture, but the way to think about it is that we're passing Mario into each of those 3 lines in succession. So think of it as gravity, dt, Mario, because where dt Mario is, dt is the new piece of information, and Mario is the current state. Similar with jump. So we're going to say jump space Mario. We're going to call that function. Physics dt Mario. And you can see that we'll just dt Mario will fit in there. And the resulting function has the type signature that we were looking for. So now we have all 3 things. We have our update function. We know how to update the state when a new piece of information comes in. We have our initial state, Mario's on the ground. And we have our input, which is time and whether we're pressing space. So putting these together, just like in the case of list fold and signal fold when we did it, it's trivial. That's it. This function produces a real-time signal that represents Mario's position over time, taking in the input of the spacebar. That's all there is. How does that play on screen? I like it. So the last step that's not that interesting is just displaying it. The only interesting part of this is the fact that we're drawing Mario in the right spot. The rest of it is just drawing the ground and the sky, and they don't move. But Mario, when he jumps, we have to draw him in the right spot, so that's what this line is, Mario Y. The other stuff is draw a blue rectangle, draw a green rectangle. Not that interesting. But it's nice that it's easy to think about because this is a pure function from the information about Mario to the information about what we want to draw. So in the 3 minutes that I have left, I guess maybe I'll go 1 or 2 minutes over. I'm just going to show you what the new stuff works like and how it's actually kind of similar to what I just went through. So this is a working example in the new style. And let me just show you it real quick what it does. It's just a counter that increments and decrements when you press up and down. It even goes negative. So what's going on here? You guys can see that, right? Yeah, that's big. The main thing to notice is that we have this update function. And it takes in a message, which you can think of as that new piece of information, and the model, which is the current state. And it, based on what the message was, it updates the model. So in this case, the model is just an integer. Our initial value, just like we had with fold, is 0. That's the initial count. And each update, we're going to update that count, depending on whether we clicked plus or minus. The one big thing that's different here, should have gone to this slide. The one thing that's different here is that there's also a view specified. And you can see that instead of using fold, we're using this beginner program thing, which is built in. And it takes in that model, that view, and that update function. And what you notice here is that there's no fold, and there's no signal. But the fundamental way of thinking about the process as new pieces of information coming in, and the update function contains everything that we need to know in order to update the state is still there. So to compare these, you can see that we have our update function. Literally, we're passing in a function called update. And it has the exact same type signature as the update function that fold P wanted. We're passing in our initial state. The difference is that instead of passing in a signal, the signal is sort of implicit. So it's not so much about the ultimate ideas that are involved here. It's more about the presentation to the user. The other big difference is that for fold, there's no display built in. We had to do our extra draw function. In this case, Elm now recognizes that when would you ever use signals without wanting to draw something to the screen as a result? So that's built into the helper function, beginner program. So the takeaway here is that fold P is still happening, and our understanding of it is still useful. It's still the right thing. But fold P is now just collapsed into the way Elm works. And as a beginner, you can get pretty far with just the implicit understanding that you need in order to understand what the update function does. And you don't have to think about multiple signals, merging them, combining them, transforming them. You don't have to think about that part. And you get virtually all the benefit of that without having to have that extra mental overhead. So kind of the way to think about it is that it's really there's one big signal. And we can fire messages into it of different types. And things in the program can listen to it. But that signal is sort of invisible, and we don't put a name on it. And that was blocking people from understanding what Elm was about. And a slightly more detailed version of that is that in that case, the input was coming from buttons that you were clicking, and that on-click event is built into the HTML library. But there are other kinds of input that you might want to take, like time. And in this case, instead of using beginner program, we're going to use a sort of more advanced thing, app.program. And this is just cutting out almost all of the program just to show the most important part, which is the subscriptions thing. We pass in, along with our initial value, our view, which is how to display it, and our update function, subscriptions, which is information about the kinds of input that we're expecting. And in this case, it's time every second tick. So that means that every time we get a second, we're going to fire a message of type tick into our program, and the update function is going to handle it. And this is really a lot like a signal. The difference is that the program at the very top level is expecting all these things one by one. And there's only one signal. There's only one stream of messages to process. And there's a lot less mental overhead that way. So the takeaway here is that it's not the abstraction itself sort of in the sky that matters. It's also how you present it to people. And another way of thinking about that is putting it in terms that Plato might have thought, which is you might know the truth, But Plato devotes just as much time to thinking about rhetoric and how you persuade people. And the way that you persuade people is things that are not really related to the truth of the thing that you're talking about. You persuade people by appealing to their capabilities, their capacities, their emotions, their prejudices. And those things are equally necessary in getting people to understand something. Thanks.